Welcome everyone. In the previous lecture, we were looking at the principle of inclusion and exclusion. We proved that, and then we looked at a couple of examples. In particular, we looked at the number of derangements using inclusion-exclusion. And then also using principle of inclusion and exclusion, we calculated the number of surjections from a set to another set. So these are the two examples that we looked. And so now let us look at a couple of more examples. What we look today is the first question is that given a multi-set, let us say a T with 3 copies of an element A, 4 copies of an element B, and 5 copies of an element C, we want to find the number of 10 combinations of this set. Which means that we want to select 10 elements, multi-sets, but of course which are multi-subsets of the set, which means that we cannot have more than 3 copies of A in the subset, 4 copies of B in the subset, or 5 copies of C in the subset, right? So what we know how to count, using the one of the results that we studied earlier is to count the number of multi-sets that we can make if there is an unlimited supply of each element. Right? So if the repetition or replacement is allowed, then we know how to do that. So given an unlimited replacement, the number of k combinations of an n element set, right? So n element, each of the element has unlimited replacement available. Then we said that it is k plus n minus 1 choose k, right? This is something that we proved. Okay, now what can we do in this case? So that is the question. So as you might have guessed, we can try to use the principle of inclusion and exclusion to deal with the question this time. So how do you do that? Okay. So first we look at S as the set of all 10 combinations where infinite replacement is available, right? So let us denote by T star the multi-set where each copies of A, B, and C are available as many as we want. Then we will define, right, as in a typical example or application of inclusion and exclusion, we define A1 to be those combinations in S which uses strictly more than 3 copies of A, right? We are only allowed to use at most 3. So the combinations that use more than 3 are going to be the bad ones, right? We want to avoid. Similarly, we can define A2 to be the 10 combinations in S that have strictly more than 4 copies of B, and similarly A3 to be the one with more than 5 copies of C, right? So now once we have this, we know how to calculate this using principle of inclusion and exclusion. We can say that, well, you take the the total number of combinations for the universe, which is S, and then you subtract the bad ones, and then you get the ones that we want, right? So what we want is that A1 complement intersection A2 complement intersection A3 complement, which is to say that we are looking at those 10 combinations which does not have more than 3A and more than 4B, or more than or more than 4B, or more than 5C, right? So none of this must be there. So therefore we are looking at A1 complement intersection A2 complement intersection A3 complement, and that is precisely by inclusion exclusion cardinality of S minus cardinality of A1 plus cardinality of A2 plus cardinality of A3, right? Subtraction from S, and then you add back the A1 intersection A2, A2 intersection A3, A1 intersection A3, right? So these things you add back. So and then you again subtract A1 intersection A2 intersection. This is what we want to do. So now all you have to do is to compute each of these quantities, right? What is cardinality of S, what is cardinality of each of these AIs and their intersections. Once we have this, we can use and then can get this one. So how do we do that here? Well, in the case what we have, k is equal to 10 and n is equal to 3 for the 10 combinations of the infinite replacement situation, right? We want to count S. So that is k plus n minus 1 choose n, which I mean choose k, which is equal to in this case 10 plus 3 minus 1 choose 10, which is basically 12 choose 10, which is 12 choose 2 also, right? Which is 66. That is easy to compute. Then what is A1, right? So A1 is the 10 combinations where A appears at least 4 times, right? Strictly more than 3. Now, if A is appearing 4 times, those are the bad guys, right? So from S, how can we compute this? Well, you look at the 10 combinations where there is at least 4, then what you can do is that you can remove these 4 guys, right? So remove the 4, and then what you get is going to be a 6 combination, right? And then it can of course contain some A's, but yeah. So but so that is okay, right? So but these are in one-to-one correspondence with each other, because you can also reverse this operation, right? So you have a 6 combination of T star where you are looking at the multi-sets using this this infinite possibility of elements, and then you add the 4 A's that back, then you are going to get 10 combinations where there is at least 4 A's, right? So therefore there's a correspondence, and then we can instead count the 6 combinations of T star. But again, counting combinations in T star is very easy, right? We already have the formula. So here it is k is equal to 6. So therefore we have 6 plus 3 minus 1 choose 6, which is 28. So similarly, you can calculate for A2, which will be 21, and A3 choose 4 is equal to 15. So these numbers we can calculate. Then what we need? Now we need to find out A1 intersection A2, A2 intersection A3, etc. Right? So these computers we need to do. So what is this? So like if you take A1 intersection A2, what we are saying is that we are looking for the the combinations where you have at least 4 A's and at least 5 B's, right? So those are the bad guys. So if both of them are happening together, then it means that 4 plus 5 9 elements are basically A's and B's. So those let us remove as in the previous case. So you will get 1 combinations in T star, so that we can count, and they are in one-to-one bijection again as in the previous case. So therefore we get it is going to be 1 plus 3 minus 1 choose 1, which is 3. So there are 3. 3 is the cardinality of A1 intersection A2. Similarly, we can find A2 intersection A3, then it will be 1, and A2 intersection, A1 intersection A3 to be 1. I think take writing mistake here. So this must be A1 intersection A3, and then A2 intersection A3 is 0, and A1 intersection A2 intersection A3 is of course 0. So we have calculated all these things, and then for therefore we can directly apply the formula. So which is cardinality of S, which is 66 minus the summation of AIs cardinalities of AIs, and then AI intersection AJ, I mean A2, etc. So that is going to give you answer 6, as we just see here. So now, so there are exactly 6 10 combinations with the property that we are looking at, right in this set, right? 3A, 4B, and 5C. Now, can you actually find the 10 combinations and list them? So that is a nice question that you can think about, and I will write it as a homework. Okay, now one more question, and then we will look at something else. Okay, so here what we want to do is to find the number of integral solutions of the equation x1 plus x2 plus x3 plus x4 is equal to 18. But then instead of the earlier conditions, right, where xi's are greater than or equal to 0 or xi's are greater than or equal to 1, right, both we solved. Here what we have is that 1 is less than or equal to x1 is less than or equal to 5, right? So there is a lower bound as well as an upper bound for xi's. And then -2 less than or equal to x2 less than or equal to 4. So this is also different, that we are allowing x to be negative, right? And then 0 less than or equal to x3 less than or equal to 5, and 3 less than or equal to x4 less than or equal to 9, right? So these are the boundary of xi's. Okay, so xi's cannot take values outside these boundaries. So now how do you look at something like this? So you think for a few minutes, you can see that, like, okay, a very simple change of variables will help you to change the format to something that we already know, right? At least partially. So let us first do the change of variables as follows. So we will say that see, x is ranging from x1 is ranging from 1 to 5, right? I want everything to be from 0 to something, right? So what I do is that I will say that y1 is equal to x1 minus 1, right? And then y2 is equal to x2 plus 2, because I again want the left hand side to be 0. So -2 becomes 0. So y2 is x2 plus 2. y3 is x3, because x3 is left hand side is 0 already. And then y4 is equal to x4 minus 3, which means that I'm going to get 0 again on the left hand side of that variable. So now if you do the change of variables, of course, you have to substitute and change the constants also, right? So then what you will get is that y1 plus y2 plus y3 plus y4 is equal to 16, right, after doing the calculations. That's that, of course, 0 less than or equal to yi, and y1 is less than or equal to 4, etc. All these conditions you added or subtracted from x's. So the bounds also changes accordingly. Now this again, right, it's very similar to the previous question, but let us first so therefore let us just look at the set of all non-negative integer solutions and then subtract using the inclusion-exclusion. So we set cardinality of S to be the, okay, so I think I wrote it wrongly. So S is to be the cardinality of S. S is the set of all non-negative integer solutions to this equation above. So since there is a one-to-one correspondence between this equation in y and the equation in x, we don't worry about the number, right? Numbers remains the same. So what is the cardinality of S? Again, applying the same rule that we did earlier, we get 16 plus 4 minus 1 to 16, the number of solutions to this non-negative integer solutions, which will be 969. That is the total number of non-negative integer solutions. But now then we have to put the other conditions on the right hand side. So how do you do that? Well, we can define the bad guys, right? A1, A2, etc. So let A1 be the solutions in S with the property that y1 is greater than or equal to 5. Okay? That is not allowed. So similarly, A2 is the solution such that y2 is greater than or equal to 7, etc. Okay? So then once you define this, okay, so I'm not doing all the details, so you can do on your own and complete the proof. So here now for each case you have to do some change of variables to reduce that counting that particular variable to be in the nice form, right? So what we are going to do is that we are going to do a change of variables again to say that okay, now z1 is equal to y1 minus 5 and zi is equal to yi for everything else. Now solutions of z1 plus z2 plus z3 plus z4 is equal to 11, right? After the change of variable will give you the cardinality of a1. And then what you do, well, this you can find out because for this equation it is basically 14 choose 11 after like 11 plus 4 minus 1 choose 11, and then you will get it to be 364. So similarly you can find a2 then a3 and then a1 intersection a2 a1 etc, and then compute this and give me the final answer. Okay, so that is a homework for you. Complete the remaining steps and solve this question. Okay, so now I will give you a few more homework questions. So let us look at one by one. So one question is that like find the cardinality of the set of all f mapping from the set 1 to m to set 1 to p such that f is an injection. Then find the cardinality of set of all f which maps from set 1 to n to x such that f is an injection and f is a surjection. Then count the number of compositions of let's say the number 40, right, integer compositions, the number 40 into 4 odd parts. Okay, so how many are there? If you are saying that okay, we want to count only the compositions into odd parts, right? Exactly 4 odd parts. Then next question is to prove that m raised to n is equal to summation k is equal to 0 to n s of n comma k mpk, right? Now for m to be a positive integer. Now suppose I let m to be an arbitrary real number instead of a positive integer. Does the identity that we gave in the part A does it hold? So if it doesn't hold, you have to give some counterexample, and if it holds, you have to prove it. Now find the number of solutions to the equation summation I equal to 1 to 4 zi is equal to 14 such that 0 is less than or equal to zi less than or equal to 8 for every I. Okay, so the next question is that in a party, right? So we already saw a similar question earlier. In a party, let's say that there are 10 men and 10 women are participating. Then there is this hat check person who collects the hats when you enter, and then give it back when you go out. Now suppose this person like just for fun maybe, right, give the the men's hat to men at random when they go back, right? Not necessarily the same hat, like pick one and then give it to the first person who comes, right? Similarly for the ladies hats also he gives only to ladies, but then again that is also at random, right? So from the ladies hats in one stand, he'll pick one at random and give it to one of the ladies who is going out. So this way he gives the hats. Then the question is that how many ways no one received their hat, right? And then in how many ways exactly two men and at least two women got their own hats? So these are the questions. Then another question is that how many northeast lattice paths go from the point 1 comma 1 to the point 8 comma 8 that does not pass through points whose coordinates p and q are both prime. And the final question is to prove that summation k is equal to 0 to n, 2k choose k into 2n minus 2k choose n minus k is equal to 4 raised to n. Okay, so that is basically what are your homework questions.